Ask someone how a sonic boom works, and they will likely describe a single, violent explosion that happens the exact millisecond a jet crosses the speed of sound. In reality, the atmosphere acts as a dense physical medium, a particle-rich fluid in continuous, chaotic motion all around us. The entire field of fluid dynamics exists to study exactly how this dense medium behaves when a solid object forces its way through it. When an object displaces this fluid, it generates acoustic pressure waves that ripple outward at roughly 767 miles per hour. Walking down the street, you gently part this air without noticing, but at high speeds, an aircraft has to violently displace tons of atmospheric mass every single second. The single explosion fallacy persists when we ignore the sky's fluid nature and the physical wave interactions it supports. As an aircraft accelerates toward that 767 mile per hour limit, it begins chasing its own acoustic footprint. Because sound waves can only travel so fast, the accelerating jet catches up to the forward-propagating waves, bunching them tightly at the leading edge. Eventually, they run out of space, merging to create a massive pileup of acoustic energy. This energy pileup prevents air molecules from moving out of the aircraft's path, forcing the jet to physically shove through a wall of its own compressed waves. This spike in resistance defines the sound barrier, an aerodynamic drag peak born from wave stacking. That stacking creates a literal physical wall of high-pressure fluid resting directly against the nose of the aircraft. We can observe this extreme pressure change in transonic flight. The visible vapor cone occasionally forming around a jet is physical evidence of this boundary. The sudden drop in pressure and temperature across that shockwave condenses moisture in the air instantly, offering physical proof of the compressibility limit. At this speed, the fluid molecules simply cannot transmit the signal to get out of the way fast enough. It is a compressibility traffic jam. The sound barrier is an inescapable density wall born from the limits of fluid communication. To go faster, the aircraft has to violently breach it. That breach occurs when the engine thrust physically overpowers the pressure wall, pushing the aircraft faster than its own sound. This exact threshold is Mach 1, the local speed of sound in that specific fluid medium at that specific temperature. We use the Mach number ratio in honor of Austrian physicist Ernst Mach, who first photographed and mathematically described these shockwaves. Above Mach 1, the air no longer smoothly parts around the airframe. It is violently shoved aside. You can observe the exact same mechanics on the surface of a lake. A speedboat slicing through deep water leaves a prominent, highly turbulent V-shaped wake trailing far behind it. That two-dimensional surface wake translates perfectly into the three-dimensional volumetric reality of the sky. Exceeding Mach 1 strips acoustic energy of its ability to expand in spheres. Instead, the aircraft drags that energy into a continuous V-shaped structure. In 3 dimensions, that V-shape is a Mach cone, a massive trailing geometric boundary of hypercompressed air. Overlapping sound waves form a rigid 3D boundary encapsulating the aircraft's wake. This angle follows a strict formula. The Mach number equals flow velocity divided by the speed of sound. As the Mach number increases, the cone radically compresses, becoming tighter and narrower. Extreme Mach cone geometry dictates extreme airframe design. The SR-71 Blackbird features incredibly sharp aerodynamics, specifically to keep the entire aircraft safely within a highly acute cone. A jet built for Mach 3 must be narrow enough to avoid intersecting its own shockwave, whereas a low supersonic aircraft can afford wider, more conventional wings. The physical boundary of this cone is so dense that it traps the explosive acoustic pressure entirely within its interior walls. A supersonic vehicle isolates itself from the air ahead, permanently dragging a rigid geometric pressure structure through the sky. Now we move our perspective from the aircraft's altitude down to an observer on the ground. We can now address the opening misconception, the idea that a jet creates a single explosion in the sky the moment it crosses Mach 1. A sonic boom occurs at the exact moment the trailing Mach cone intersects with the Earth's surface. The geometry of the cone violently drags across the terrain, creating a boom carpet roughly 1 mile wide for every 1,000 feet of altitude. If an observer in City A and an observer in City B are 50 miles apart along the flight path, they will hear the exact same boom at different times as the cone sweeps over them. The boom is actively occurring every single second the aircraft maintains supersonic flight. In reality, it is a continuous spatial event dragged over the observer, completely dismantling the idea of a temporal, one-time explosion. When that cone sweeps over you, it leaves a specific acoustic signature, a distinct double boom. We can identify why one aircraft produces two distinct kinetic impacts on the ground by looking at the pressure profile. This graph illustrates the N-wave profile: an abrupt positive spike, a linear downward slope, and a sharp negative return. The positive spike correlates directly to the nose violently displacing fluid. The negative return correlates to fluid rushing back together at the tail. The jet is actually dragging two distinct, overlapping Mach cones, a bow shock wave from the front and a tail shock wave from the rear. The physical length of the aircraft determines the millisecond delay between these two overlapping impacts. The sonic boom represents the inescapable geometric footprint of an object traversing a fluid faster than its own information speed.